Assalamu alaikum. Welcome to lecture 4. We continue. We were studying sieve analysis. We spoke about particle size distribution curve. Remember this particle size distribution curve. So we found that after sieving the sample, we collect all retained weights. We change them to percent passing. Then there is a relation between diameter, this is diameter in millimeter, log scale, and percent passing from 0 to 100. Okay? Now, if you look to the particle size distribution curve that we studied last time, the example that we studied, and even this picture, you see, this figure. You know, sieve number 4. What is the opening of sieve number 4? Good. It's the borderline between gravel and sand. Okay. 1, 2, 3, 4, 4.75. This is right. This is gravel, and here we have sand. Okay. Sand ends at number 200, which has an opening of 0.075. Right. Okay. 0.075. 0.01, 2, 3, 4, 5, 6, 7, 5, 0.075, this is 0.075, right? So, here we have sand, right? Here we have gravel, and here we have fines, silt and clays. Now, last sieve that we used in sieve analysis, it's number 200, right? Number 200, last sieve. In the example we took previous lecture, we found that 62% of the sample passed number 200, right? 62% of the sample, it is fines, right? It consists of smaller particles, fines. 62%. The sieve analysis, it gives us only the distribution of sand, you see? Right? It gives us only the distribution of sand. Because first sieve is number 4, last sieve is number 200. Of course, it gives us that we have, for example, 10% gravel, 20% gravel, maybe 30% gravels, even if we had 100% gravel, but it has no more information about the gravel, right? So it gives us only percentage of gravels. Understood? We have only the percentage of gravel, but we don't have any explanation. What is this gravel? Is it 4.75 only? Is it 5 millimeters diameter? Is it 8? We have no information, right? Just the percentage of gravel. And also, it gives us the percentage of fines. Like, for example, we had 62% fines. Remember in the previous example. But what do we know about these fines? Are they silt or clay? We don't know, right? Because the first is number 4, the last is number 200. Then what we are doing actually is classification of sand only, right? It's just for sand to know if we have poorly graded sand, if we have whatever, right? But we don't know anything about gravel except the percentage, and we don't know anything about fines except the percentage, right? Correct? Are you sleeping? It's very hot? Yes. It's very hot. It's very hot. It is very hot. Let it be 22 enough. Otherwise, they are already sleepy, including me. We have a problem. Sieve analysis describes the distribution of sand only. It gives us percentage of gravel, percentage of fines, but no other explanation, right? Okay, if we are dealing with 10 or 20% of gravel, I can describe gravel by visual description, right? Because it's big. Okay, I can say that I have huge particles or huge stones. I can say that I have small particles with almost 10 centimeters in diameter. I can describe them visually, okay? So I don't care how much the percentage of the gravel, I will describe them. But the problem with fines, it is with fines. Especially if we have, like in our previous example, 62% of the sample is fine. This is, I cannot just ignore it saying that it is fines. Because if this 62%, out of them 2% silt and 60% clay, it's a problem, right? We saw that bentonite, it has high swelling, high activity, high plasticity, high compressibility. Remember that? So we just cannot ignore. We cannot ignore that. Just by doing sieve analysis, we solve the problem. We have to know how much sand, how much silt, how much clay. Okay? In some cases, we may have 100% of the sample fines. We just cannot say that, okay, we have 100% fines. I have to know how much silt, how much clay. Okay? So what we have to do? Sieve analysis is not suitable. Because the last sieve that we had, number 200, maybe not number 270, as you saw. We had number 270, right? But still it doesn't reach clay. Why we don't do some smaller sieves? You know that, remember, clay smaller than 0.001 millimeter, right? We said that. Clay is smaller than 0.001 millimeters, 1 micron. So we need the sieve that the opening of it is still less than 0.001 millimeter. Why impossible? It was impossible at the time of my grandmother, when she invented the sieves. She used them to make, bread, ma'mool, at the time of Eid. Right? Maybe it was impossible 100 years ago, but you know that computers now are capable of doing many things. We have cameras smaller than that diameter. We put it in the body of a person, right? We put it in his veins, in his organics, okay? And we make pictures inside the body of a person, right? Even we do some kind of surgeries, right? Like, for example, what we call it al-qastara. Okay? So it may be not very it may be not impossible for new technology to develop sieves with the smaller openings. So why we don't use them? Why we don't invent more sieves with smaller openings?
More than one particle be combined with each other. We cannot pass it through the opening.
Maybe you are right. Yes, correct. The problem is not with the sieves. The problem is with clay and silt particles. Once they get smaller, you will not have a particle alone. You see, if you put your hand in the sand, okay, get some sand in your hand, open your hand, then the sand fall down, right? I can pick a particle of sand, right? I can see this is one particle of sand, right? But you cannot do this with clay, because clays are all together always. They are all together. They are not just one by one. There are groups of clay particles. Why? You see, who has a bigger particle size, clay or sand? Okay. So if we had, for example, a particle size of a sand as big as this room, so the clay may be as small as this piece. Okay? You remember, from 4.75 to 0.075, this is sand. But we are talking about less than 0.001. 0.001 is the beginning, still less than that, okay? So it's very small. Once it's very small, then the weight is smaller, right? The weight of clay is much less than the weight of sand. But once we have many particles, many small particles, their specific surface is bigger, greater, or less than a bigger, greater. So we have specific surface, huge, okay, great. So the charges on the surface is greater. So its ability to bond, to attract other particles is more, okay? So between clay particles we have strong bonds. Between sand particles we don't have strong bonds, okay? That's why you can pick a particle of sand, but you cannot pick a particle of clay, if you can even see it, because you will not see it. So the problem is not with the sieves. The problem is with clay. It's with fines, that you will not find a particle alone. You will have them all together, maybe 17 particles together forming just one look-like particle. It's not a particle, it's 17 together. It's maybe 100 together, okay? So here, if we did the sieve analysis, we will deceive ourselves. We thought that one particle passed, but it's not one particle. It's 17 particles passed together in one group. You see? So this is the problem. That's why sieve analysis is not suitable. Okay? So what we have to do? We just cannot ignore the problem, even if we don't have enough sieves. We go to another test. Okay? We go to another test. So, it's obvious that sieve analysis is used for classifying sand only, as I described. See? Sand only. For clay, otherwise it will be angry. Okay? For clay, we have to do hydrometer test. We call it hydrometer test, even in Arabic, hydrometer test. Hydrometer test. By the way, this is one of the tests that you have to do in the lab. Okay? You did water content? You did any of the experiments? Okay? You did water content, specific gravity. After that, you will do sieve analysis. Did you do sieve analysis? Not yet. After doing sieve analysis, you will do the hydrometer test. So I will not explain it. I will just give brief glimpses. Okay? Just brief ideas, brief hints about the hydrometer test. Okay? Hydrometer test, first of all, it is based on Stokes law. Maybe you heard about Stokes law. Did you hear about it in physics, in fluid? Stokes law. Did you hear about it? In fluid. In physics, maybe, at school. That's right. Particles or objects settle in liquids proportional to their weight, to their mass. We know that. Okay? When we have heavy material and light material, okay, we put them all in liquid. The heavier will go faster. It's obvious. Try it when you swim in a pool. Okay? One heavy weight, one tiny. Okay? And then you jump in the water and see who will reach the bottom first. Okay. Stokes' law says that heavier particles, heavier soils, heavier objects, heavier objects will settle faster than light ones. That's it. Easy. We will use this law. Okay? We will use it. We will benefit from it in doing hydrometer test. In hydrometer test, guys, we will bring one 1,000 milliliter equipment like this, you see? This is a cylinder, glass cylinder, okay? And we will put water, 1,000, okay? So this is filled with water, 1,000 milliliter water, okay? Then after that, I will take from it 40 milliliter and throw them away. Or you can put from the beginning 960 milliliters, okay? We have now what? We have 960 milliliters of water, okay? Now, the idea is when we put soil, fines, which passed number 200, okay? By the way, those soils which will pass number 200, they are almost like dust. You will see this. They are almost like dust. I will weigh them, and then I'll take them and put them in water. Once I put them in water, they will settle, okay? The heavier will settle faster, and I will see the change in color. You see? You will see the change in color. And after a while, you end up with, like when you look at a cup of cacao, cappuccino, choco, whatever. You'll see if you lift it for a few minutes, then you will find that below, at the bottom, it's darker in color than above. Remember this? Why it's darker? Because things settled, okay? Things settled down. So we will find different in colors. Here the same thing. We will find difference in colors because we will find that here it's like brown, dark brown. Here it's light brown, or maybe closer to the white, to the color of water. What color is water? Okay. See, so we will see particles when they are settling. Now the speed of settling depends on particle size, right? Once we are dealing with very small particles, can we substitute particles weight to particles diameter? Can we? Can we? Instead of using particle weight, particle mass, we will use particle diameter because we are dealing with very small particles in Arabic. إذا احنا بنتعامل مع أجسام صغيرة جدا، هل بإمكاننا نستعيض عن التعبير عن وزن العينة، وزن الحبة بقطرها؟ نقدر. ليش لا؟ لأنها صغيرة. لأنها صغيرة. هي مش حجم هالقد من الفلين مع حجم هالقد من الحديد. لا، احنا بنتعامل أول شيء مع مادة واحدة، سويل، رايت؟ ومش بس هيك، وكلياتهم حبات صغيرة، يعني بالتالي ما في مجال لفجوات هون ولا فجوات هنا. بالتالي ممكن نعبر عن حجم الحبة، عن الماس، عن وزن الحبة بقطرها، صح ولا لا؟ إذا هون رجعنا للقطر مرة ثانية. Which is important for us because the curve, you remember, it has diameter, right? Diameter versus percent passing. طيب percent passing منين بدي أجيبها؟ By using Stokes law and some other equations, we change the speed of passing, the speed of settling, we will reach percent passing, okay? So we end up with percent passing with diameter. Again. See, of course, there are equations that you will use. I told you I will not explain everything. But what if group of particles settle together in water? It may happen, right? It may happen. So what we have to do? We have to make something to make every particle settles alone. How we do this? We add a chemical substance, okay? Chemical substance. It's called only. خلاص. Hexametaphosphate. It's called hexametaphosphate. It's a chemical substance. We call it dispersive agent. Dispersive agent. You know what is disperse? Disperse. Please, disperse. Or without please. Disperse. Go away from each other. Okay? Disperse. Don't be together. Disperse. Like you do a demonstration in Midan al-Tahrir together. Disperse. Okay? Disperse. In Arabic it's called ifranqi'u. You know ifranqi'u? You don't know ifranqi'u? Go away. It's said in the old Arabic tradition. يقال إنه جحل تم عليه مجموعة من الناس وكان يتقعر في اللغة. يعني إيش يتقعر في اللغة؟ يعني بيختار غريب الألفاظ زي غلام أبو علقمة. هذا أبو علقمة كان يتقعر في اللغة، دائما يختار غريب الألفاظ ويحكي ما حدا بيفهم. المهم فبيقول التموا عليه مجموعة فقال ما لكم تكأكأتم علي كتكأكئكم على ذي جنة افرنقعوا. تعرفوا تعيدوها؟ كيف لو حكيتها بالإنجليزي هذا؟ ما لكم تكأكأتم علي يعني التميتوا علي كتكأكئكم على ذي جنة يعني على واحد مجنون. كيف بتلتموا على واحد مجنون؟ افرنقعوا يعني حلوا عني. افرنقعوا يعني انتشروا. فهو هيك أبو علقمة كان يستخدم هيك ألفاظ غريبة جدا. في يوم من الأيام موظف واحد عنده مسكين على قد حاله يعني أنجأ يعرف اللغة العادية. فلما أجى ينام بيقول له يا غلام إذا أسقعت العتاريف أيقظني. ونام. شو أسقعت العتاريف؟ مش فاهم هو. وبعدين صحى أبو علقمة وقال ويحك يا غلام هل أسقعت العتاريف؟ قال زقفيلم. طلع اشطر مني. منين هاي زقفيلم؟ هاي ما مرت علي. قال يا غلام ما هي زقفيلم؟ قال وما أسقعت العتاريف؟ قال يعني أسقعت العتاريف يعني صاحت الديكة. قال زقفيلم يعني لم تصح. فخلص بطل أبو علقمة يتقعر في كلامه وبطلت أنا أحكي إنجليزي. المهم hexametaphosphate dispersive agent مادة مشتتة، مادة بتدمر العلاقات البوندز. أوكي علاقات الشد بين الحبات فبصير كل حبة ده وحدها. dispersive agent hexametaphosphate. أعطيكم معادلتها الكيماوية؟ بلاش مش ناقصكم مصايب. خلاص مش بحاجة. hexametaphosphate dispersive agent.
المادة
هلا بنضيفها للمي. فاحنا اخذنا بنضيف 40 مليلتر. 40 مليلتر 40 مليلتر و960 مليلتر 1000. So we have 4% right hexametaphosphate 4% right. طيب do we have always to use 40 milliliter 4% hexametaphosphate? Now it comes your engineering judgment, engineering sense. If I found that I'm dealing with very strongly bounded particles, so I may put 10%. Once I put 25%. Okay? So it's up to the case I have, right? You will use in the lab, you will use 4%. Okay? But you have to know that you shouldn't die using only just 4%. Because once you studied at school that you should use 4%. No, it's up to the case. Once I did an experiment, I used bentonite. So I had to use 25%. You see? Okay, now we will add dispersive agent to the water from the beginning. Okay, so we have here 1000 milliliter of water and dispersive agent hexametaphosphate. 960 milliliter of water, 40 milliliter of hexametaphosphate dispersive agent. Now we have 1000 milliliter of water. We bring the soil, which is almost dust, and put it here. And okay, we begin. We will begin. we will begin. We have to know how fast this soil will settle, right? How we will know that? Here it comes the hydrometer. By the way, hydrometer test, because we will use hydrometer. Hydrometer is a piece like this. You see? It has storage here, and then it has number. Okay? It has numbers here. When we put this in the water here, it will sink. Okay? Then we will write the number that we reached. It was this number. Okay? Now, if we put the soil here, the soil will prevent the hydrometer to sink, right? So it may sink only to here. We will have this number, right? Once the soil begins to settle, as the soil goes down, the hydrometer will go down, right? فاهمين؟ هيدروميتر زي ميزان الحرارة بس 15 سنتي أو 18 سنتي. أوكي؟ والستوريج تبعته حوالي الثلث. بنحطه في المية طبعا بده يغوص لحد معين وبعدين بيطوش. فأنا باخد هذه القراءة. بس بعد شوي لما بحط التربة وبحطه طوالي ورا التربة، هو حيغوص مش لقد ما غاص أول، لأنه التربة حتمنعه، صح ولا لا؟ لساتها التربة على السطح حتمنعه، فحيغوص لحد أقل شوي، صح؟ وبعدين مع الوقت بتبدأ التربة تغوص. كل ما غاصت التربة كل ما الهيدروميتر لحقها بيغوص معها. فإذا أنا بقدر أخذ علاقة زمنية مع القراءة المتغيرة هون، صح؟ first minute خذ القراءة يا شباب. second minute خذ القراءة يا شباب. at time 4 minutes خذ القراءة إلى آخره. ماشي؟ عندكم جدول وموجود في أزمنة محددة، وبناخذ إحنا القراءات وبنحطها، وهاي القراءات في معادلة بسيطة بتتحول ل percent passing. أنا عبرت عن الهبوط بما إنه اللي أكبر بهبط أكتر، إذا ربطت الهبوط بإيه؟ بسرعة هبوط الهيدروميتر بقراءة. صار في عندي زمن مع قراءة، مش هيك؟ وبطريقة بسيطة بتحول عند الموضوع إلى percent passing. هاي الفكرة الرئيسية. أنتوا حتعملوا التجربة وأنا مش راح أشرحها كلياتها، بس فهمنا شو الفكرة. بنحط الهيدروميتر هون، بنحط التربة بوجود الديسبيرسيف ايجنت تتشتت عن بعضها البعض، وما علي إلا أن أجي 1 2 3 بخض المية، الأنبوب هذا أنبوب الاختبار، بخضه بميته والتربة بتاعته، وبحطه ومباشرة بس بحط عليه إيش؟ الهيدروميتر. 1 2 3 يلا خذ القراءة الأولى، وببدأ أخذ قراءات لفترة طويلة، وكل مرة بلاقي الهيدروميتر ماله بينزل. باخذ هذا الكلام وبعمله في المعادلات، بيطلع معي percent passing. بس يا شباب في مشكلة. لازم أخذ في الاعتبار 3 شغلات وأنا بعمل هاي التجربة. أنا راح أحكي لكم عنها بالمختصر بالاسم، بعدين أنتوا حتعرفوا كل واحدة كيف حتعملوها. أول حاجة لازم أخذ الزيرو كوركشن. إشي اسمه زيرو كوركشن. شو هو؟ اللي هو العلاقة أو حاجة متعلقة بإني أنا لما بحط الهيدروميتر في المي لحالها بيعطيني رقم، ولما بحطه في المي والتربة في أول لحظة بيعطيني رقم مختلف، صح ولا لا؟ هذا اسمه زيرو كوركشن. بدي أعمل هناك بعض الشغلات حتعرفوها في المختبر، واضح؟ إذا في عندي إشي اسمه زيرو كوركشن، لازم أول شيء أخذه في الاعتبار. الإشي الثاني إنه هاي التجربة مصممة على أساس يكون درجة حرارة المختبر 20، مش زي ما قبل شوي 50. 20. هلأ لحظة شوي، هل السوائل إلها علاقة بالحرارة؟ في حاجة اسمها فيسكوسيتي، الميوعة. طب كل ما زادت الحرارة شو بصير في الفيسكوسيتي الميوعة؟ كل ما زادت الحرارة بتزيد الميوعة، وكل ما زادت الميوعة سرعة الهبوط بيزيد، صح ولا لا؟ طب إذا أنا عملت التجربة، الأصل التجربة تكون في درجة حرارة 20، وبعدين أنا درجة الحرارة عندي في المختبر الآن 50 زي قبل شوي، معناته إيه؟ معناته في فرق، صح ولا لا؟ طب لنفرض إنه ما قلنا لهم مش يشغلوا التدفئة وضلت درجة الحرارة زي برا 7 أو 8، معناته صارت الميوعة أقل، معناته سرعة الهبوط أقل، صح ولا لا؟ إذا لازم أخذ هذا الكلام في الاعتبار. هذا بنسميه إيش؟ Temperature correction. You have a table in your handout which is related to the laboratory. Okay, you have a table with different temperatures and different corrections. Okay, you just have to find what is the temperature of the room and then go to the table. You will find what is the correction. Okay, then we have to have meniscus correction. Meniscus correction. Meniscus correction. يا شباب تذكروا انه لما بنحط سوائل في اوعية زجاجية سطح الماء على سطح الماء بيكون مستوي ولا بيكون مقعر؟ باخذ شكل تقعر. ليه؟ في عندي الخاصية الاسموزية، في عندي الخاصية الشعرية، في عندي التجاذب بين سطح الزجاج وبين الماء، صح ولا لا؟ فبيكون السطح بهذا الشكل زي ما احنا شايفين هون، مش هيك؟ يكون السطح زي هيك، مش هيك؟ طيب بس بما انه لون السائل هو لون ايش؟ بني، صح؟ لون بني. وانا عادة كنت ايش بعمل؟ بطلع من هون وبشوف وين السائل واصل وباخذ القراءة، مش هيك؟ تخيلوا هذا الكلام. فالقراءة اللي راح اخذها هي هون، بينما القراءة الحقيقية وين؟ تحت. دائما في فرق بين القراءة اللي انا ماخذها والقراءة الحقيقية. هاي اسمها المنسكس. ماشي؟ كيف بدي اخذها وكيف بدي اعتبرها موضح عندكم ومشروح. ماشي؟ انا بس نبهتكم ل 3 corrections: zero correction, temperature correction, meniscus correction. Okay? We'll take this into consideration. Then after solving the equation that we have, we end up with what? We end up with diameter versus percent passing, right? Which we had before. So we plot this. So we end up with this. Suppose this is 1, okay? This is 0.1, this is 0.01, this is 0.001, okay? Now, percent passing number 200, 0.075, 0.075, here is 0.075, 2, 3, 4, 5, 6, 7, 5, so this is here. It was 62%, but maybe it was 100% then there. Okay. Then we go to to describe how the sieve is, how the particle size distribution curve is. Okay. But of course, listen. When we do the hydrometer, the total weight, which we will put in the hydrometer, how much? In the previous question, remember? You go back to your previous question. How it was? How much it was? 280, 287, the last number. Previous example that we took. You didn't write it? Sieve analysis. Okay. In the example we had before, we had it, I think it's, which is 62% of the 450. It's around 282 grams, okay? Now, then we begin with 282 grams, okay? This is 100%. So if we draw the curve, we will end up with like this. Remember? And up to 62, right? And then we continue from 100 like this. Then we had two curves, which is wrong. What we will do? After finishing everything, instead of considering the 62% as 100%, we change it to 62% and we continue. Then we end up with one particle size distribution curve. Up to 62, then we continue like this. Okay? Remember this. Because in some books, they explain sieve analysis alone, hydrometer alone, and then the hydrometer begins from 100%, which is not correct. If we have to end up with one particle size distribution curve, so it begins from the beginning, which was at our time 16. Number 16, we began with, number 10, we began with 0, right? Number 10. To finish at the end. Okay, we will have one curve. Okay, so we will end up with having this. We will end up with one curve. That curve begins from 10 to 0.001 and more. Okay? And at that curve, of course, in this case, we will find what? We will find how much gravel, how much sand, how much silt, how much clay. Right? Suppose that we have, this is the gravel, and this is the sand, and this is the silt, and this is clay. And this is a particle size distribution. Don't look at the numbers here. Okay? This is a particle size distribution curve collected or obtained from sieve analysis and hydrometer. Okay? Just by look, we say that we have no gravel, we have sand as much, we have silt as much, and we have the remaining clay. Okay? So by this way, we end with knowing the percentage of everything, hydrometer, by using sieve and hydrometer, sieve analysis and hydrometer. We know that how much we have gravel, how much sand, how much silt, how much clay. And then after that, of course, I can obtain Cu. What is Cu? D60 over D10, which is we call uniformity coefficient, right? And C sub Z, which is coefficient of gradation or coefficient of curvature, D30 squared by D10 and D60 multiplied by D60, where D10 is effective grain size. Remember, effective grain size. Now, after drawing all this picture, I come here. D60, I need it. Okay, here is D60. I found this number, D60. Okay, D30, I need it. Here is D30. I found this number. D10 is needed. Here is D10. I found it. And you see that always D60 is bigger than D30, bigger or greater than D10. Okay, we take these numbers and we say, okay, D60 by D10, this is Cu. Okay, D30 squared by D10 and D60, we get C sub Z. Okay, then what? If I get, for example, Cu equals to 4, Cu equals to 1, Cu equals to 7.5. What is good for you? What is bad for you? What's the meaning of 4, 3, 1, 7? How can I benefit from Cu and C sub Z? How can I benefit from it?